Welcome. In this video presentation, we'll cover topics that many technicians feel are very important: the diagnosis, tune-up, and repair of automotive engines. This presentation is designed to help you prepare for and improve your chances of passing the ASE Engine Performance Test A8. The ASE A8 test is divided into 6 parts: general engine diagnosis, ignition system diagnosis and repair, fuel, air induction, and exhaust system diagnosis and repair, emissions control systems diagnosis and repair, computerized engine controls diagnosis and repair, and electrical systems diagnosis and repair. In this presentation, we'll take a diagnostic approach to the topics in the ASE task areas. Since not all individual tasks are covered in this video, use the available reference books such as manufacturer's service manuals, technical training manuals, textbooks, and ASE study guides to help bring you up to speed on any area that you need help in before taking the ASE A8 test. After viewing this presentation, you should be able to use a variety of diagnostic tests to determine the cause of various engine malfunctions, diagnose and repair ignition-related problems, diagnose and repair fuel, air induction, and exhaust system-related problems, diagnose and repair emissions control systems related problems, diagnose and repair computerized engine controls related problems, and diagnose and repair engine electrical system related problems. Most technicians will begin their diagnosis of an engine drivability or performance problem on an OBD or OBD2 equipped vehicle by checking for stored diagnostic trouble codes. First, locate the Diagnostic Connector Link, or DLC, and connect the scan tool. Use the protocols in the scan tool to check for any stored diagnostic trouble codes, also known as DTCs. If a code or codes are displayed, record the DTC. The scan tool will display information as to whether the code was set on the current trip or when it happened in the past. Record that information as well. Then use the Scan Tool menu to enter the Freeze Frame Data function. Freeze Frame Data will give you the operating conditions under which the primary stored DTC occurred. Freeze Frame will only store the highest priority DTC. Freeze Frame Data will give you the engine RPM, calculated load value, engine temperature, and vehicle speed, as well as other specific information that will allow you to operate the vehicle under the conditions that the code occurred. Clear the DTC, then operate the vehicle under the conditions recorded on the freeze frame data. Road testing is often required to duplicate the DTC. Whether or not you are able to duplicate the DTC, continue your diagnosis by reviewing the diagnostic procedure in the service manual. OBD2 equipped vehicles use the PCM to monitor the sensor input signals and the operation of the output solenoids and actuators. The systems are monitored for 3 types of faults. The first is a normality check of the circuit to confirm that the sensor or actuator circuit is not open or shorted. The second test is for the operation of the sensor or actuator within its normal range of operation. The third test is a rationality test to determine if the sensor signal is reasonable when compared to other indicators of engine performance. If the PCM detects a failure of a sensor or actuator to meet any of these criteria, it will store the conditions under which the fault occurred in freeze frame data. In most cases, the malfunction indicator lamp will be illuminated on the second consecutive test failure. More often than not, the problem in a monitored circuit lies with a loose or corroded connection or a problem with power supply or ground. In most cases with DTCs, you will have to use a digital multimeter to check the reference voltage to the sensors and the return voltage to the PCM. The ohm meter function can be used to test the resistance and continuity of the sensor. Voltage drop tests should be done across connectors and components to check for excessive resistance that could alter sensor input or actuator output signals. Once you have verified that your repair is complete, make sure that you connect a scan tool and clear any codes that may have been generated during your repair. In many cases, you will have to drive the vehicle in a specified manner to verify that the problem has been corrected. This is called a drive cycle. Once you have completed all of the required driving cycles, the MIL is not illuminated, and if there are no current or pending DTCs, the vehicle can be returned to the customer. If you don't find any stored codes, then begin your diagnosis of the engine performance problem in the same way as you would for a non-OBD2 equipped vehicle. The diagnosis of engine performance problems begins with the basics. That's why almost every major manufacturer publishes a basic inspection procedure. Start your diagnosis with a road test to confirm the drivability concern, then do a good visual inspection, looking for loose, cracked, or misrouted vacuum lines, bent or kinked fuel lines, loose electrical connectors, and the condition of the air filter and intake bellows. If any abnormal condition is found during the visual inspection, repair it, then continue with the basic inspection. If everything looks okay, connect a tachometer or a timing light and check the engine idle speed. Too often, drivability problems such as hesitations, stumbles, stalling, and improper transmission shifts are simply the result of an improperly adjusted idle speed. Many manufacturers have specific sequences to set the idle speed correctly, so make sure to follow the procedure for the vehicle you're working on. When the idle speed is set correctly, move on and check the timing. Timing is adjustable on vehicles equipped with conventional or high-energy distributor ignition systems. Most distributorless or DI ignition systems do not have a timing adjustment. Retarded timing can cause problems with hesitation, backfires, poor idle, hard starting, and engine overheating. Overly advanced timing can cause a lack of power, hard starting, high-speed misfires, starter drag, and detonation. A timing check will also tell you if you have a worn timing belt or a belt that has jumped time. The base adjustments for timing and idle are crucial to engine operation on today's vehicles because those settings are the starting point for any engine control system's fuel and timing management programs. If the base adjustments are off, everything else that follows will be off. If you're dealing with a concern of a rough or uneven idle or low power, pull the spark plugs and do an engine compression and cylinder leak down test to confirm that the engine internals and valve train are not the cause. If the basics are all within spec, then move on to confirming the operation of the ignition, fuel, and emissions control systems. A road test of the problem will probably give you a clue as to whether you're dealing with an ignition or fuel problem, so where you start is dependent on the complaint. Ignition systems diagnosis is a logical next step for problems with misfires, backfires, no start conditions, or engine knock. An oscilloscope secondary ignition pattern is the best way to check the proper operation of the ignition components. Most vehicles that use a distributor today use a transistorized ignition module to switch open and close the primary circuit. The transistor base is supplied a small amount of current from a triggering device that allows current to flow through the coil primary circuit. When the triggering device switches the control current to the transistor off, the magnetic field in the primary coil winding collapses and induces voltage into the secondary circuit to fire the plugs. Position sensors that determine the crankshaft position are used to control the flow of current to the base of the switching transistor. These sensors can be magnetic pulse generators, Hall effect sensors, photoelectric sensors, or metal detection sensors. If there is a failure of a position sensor or part, the trigger function will be lost. Shorted triggers will supply current to the switching transistor all the time and cause the coil to overheat before going open. Open triggers will leave the primary circuit open and no power flowing to the coil. A digital oscilloscope is the best tool to check the pattern on the triggering device, such as the crankshaft position sensor on an OBD2 vehicle. Misfires can occur if the sensor signal is intermittent. If the crankshaft position sensor signal is okay, continue your oscilloscope testing with ignition patterns. The ignition patterns between conventional and HEI ignition systems are similar, but for the breaker point oscillations that are absent on the transistorized ignition pattern. The ignition pattern shows the firing line spike when the ignition primary circuit is opened by the PCM signal and voltage is induced into the secondary coil windings that results in the spark plug firing. The firing line may be followed by a series of oscillations as the remaining energy in the coil is dissipated after the spark plug is fired. HEI systems use capacitors or diodes to capture these oscillations to protect the PCM, and the result is a smooth transition to the point where the ignition module closes the primary circuit. The pattern for all cylinders should be the same. Any abnormal pattern will point you to the cylinder or component responsible for an ignition misfire. Uneven firing voltages between cylinders indicates problems with spark plug cables or a worn distributor cap, or a vacuum leak or open EGR valve that affects only one or two cylinders. Higher than normal firing voltages for all cylinders can be due to retarded ignition timing, a lean fuel mixture, or high resistance in the coil wire or coil tower or distributor cap. And if the cause is retarded ignition timing, don't overlook an over-torqued Knox sensor that will retard ignition timing. Higher firing voltage for one cylinder can result from high resistance in the spark plug cable, a defective spark plug, or corrosion on the spark plug terminal. Abnormally low firing voltages for all cylinders are usually caused by rich fuel mixtures, low coil output, or low engine compression. Low firing voltages that affect only one cylinder can be caused by an arcing ignition cable or coil, or by a fouled spark plug. Normal but inverted patterns indicate reversed coil polarity. A cylinder with no firing voltage can have a cracked distributor cap terminal, shorted plug wire, or fouled or defective spark plugs. Distributorless or EI ignition systems have similar patterns but use an ignition module integrated into the PCM to trigger individual or shared coils to fire the individual spark plugs. EI systems also use a camshaft position sensor to determine when the cylinders are at top dead center. Initial ignition timing is not adjustable on most EI-equipped vehicles as it is a function of the PCM software. On distributorless ignition systems, the primary circuit is the power feed from battery positive and is checked with a multimeter for voltage and continuity. Diagnosis of drivability concerns that are other than ignition misfires start with a test of the fuel system pressure. Always exercise extreme caution when working on pressurized fuel systems and always wear eye protection. Depressurize the fuel system by removing the fuel pump fuse and then start the engine. Allow the engine to run out of fuel and stall, then install the fuel pressure gauge. Reinstall the fuel pump fuse and test the fuel pump. On some systems, you will have to disconnect the vacuum line to the fuel pressure regulator. Cranking fuel pressures are usually at the maximum rating for the pump. Connect the vacuum line to the pressure regulator and run the engine. Most fuel-injected vehicles have an operating pressure between 35 to 50 psi. Check the specs for the vehicle you're working on. Excessive fuel pressure results in a rich fuel mixture and may cause problems with engine flooding, excessive emissions, hesitations, and poor fuel economy. Low fuel pressure may cause lean mixtures, hesitations, hard starting cold and hot. Low fuel pressure can result from a defective fuel pump, excessive resistance in the fuel pump circuit, a restricted fuel filter, or a faulty fuel pressure regulator. If the fuel pressure is within specification when cranking and running, shut the engine off and monitor the ability of the system to hold pressure. Any loss of pressure within 2 minutes of shutdown indicates a leaking or hung injector, or possibly a defective fuel pressure regulator. If the fuel pressure is okay and the injectors are not leaking, do a cylinder balance test using a scan tool. Use the scan tool to disable the injector for each cylinder and monitor the engine RPM drop. There should not be much more than a 50 RPM drop for each cylinder. If there is no drop, the injector may not be opening, or the injector may be clogged or restricted by carbon buildup. A quick test to see if the injector is working is to use a stethoscope to listen for the injector click. If it's not clicking, the coil may be open, or there may be a problem with the injector signal from the PCM or the wiring. If it is clicking, then use a digital multimeter to check for voltage at the injector. Voltage drops across the circuit can show high resistance that can cause a lower than normal voltage at the injector. An ohm meter can be used to check the injector coil resistance. A digital oscilloscope or pulse duration meter can be used to read the injector on time in milliseconds. Higher than normal pulse durations indicate a rich command from the PCM. Lower than normal pulse durations indicate a command to lean out the mixture. The pulse duration should cycle between rich and lean. If the engine is running continually rich or lean, the source of the problem must be further diagnosed. Continually rich commands may result from a lean heated oxygen sensor signal to the PCM. Lean signals result from vacuum leaks, malfunctioning secondary air systems, or exhaust system leaks before the sensor, or from a contaminated oxygen sensor. A malfunctioning mass airflow sensor or manifold absolute pressure sensors can also affect the mixture commanded by the PCM. A continually lean signal from the PCM indicates a rich reading by the heated oxygen sensor. Rich conditions often result from malfunctioning coolant or intake air sensors or a bad mass airflow sensor. Internal engine problems such as worn piston rings can also cause continually rich conditions. If the ignition and fuel systems check okay, use an exhaust gas analyzer to get a picture of how the engine is performing. Exhaust gas analyzers can be used to diagnose several different conditions such as a rich or lean mixture, leaks or restrictions in the exhaust system, and even a leaking cylinder head gasket. Exhaust gas analyzers measure the amounts of HC, CO, NOx, CO2, and O2 in the exhaust stream. The optimum fuel mixture for emissions performance is the stoichiometric point of 14.7 pounds of air to 1 pound of fuel by weight. For a catalytic converter to operate efficiently, the mixture must cycle from rich to lean at least 5 times every 10 seconds. Lazy O2 sensors can cause problems with hesitations and surging. High HC readings result from incomplete combustion and lean misfires. High HC readings can cause damage to the catalyst as they are an indication of unburnt fuel. The catalyst operation is monitored by the rear-heated O2 sensor. The signal should vary over time from rich to lean to rich, but much slower than the front HO2 sensors. High CO readings result from rich mixtures. High NOx emissions result from high combustion chamber temperature. An inoperative EGR valve is the most likely cause, but don't overlook engine overheating. The EGR valve can be checked by different methods depending on whether it is vacuum or electrically controlled. Using a vacuum pump or scan tool, depending on the application, open the EGR with the engine idling. The engine should stall. If it doesn't, the valve is inoperative. If the signal to the EGR to open is present, remove the EGR valve and check for a bent shaft, bad diaphragm, or a carbon buildup that is restricting flow. For electronically controlled EGR valves, use a digital multimeter to test for available voltage and do voltage drop tests to isolate high resistance in the circuit. If everything looks okay, check to see that exhaust back pressure is available for the EGR to work. A low NOx reading could indicate too much back pressure. If you suspect a restricted catalytic converter or other exhaust restriction, you can perform a back pressure test using a vacuum gauge. Hold the throttle at 2,000 RPM, then let go. If the reading is sluggish, returning to normal, you can suspect an exhaust restriction. Lastly, don't overlook the PCV valve. Check the PCV system by placing your thumb over the PCV valve inlet with the engine at idle. If you feel little or no vacuum, check the PCV valve, hoses, and fittings for restrictions or leaks. Gently shake the PCV valve to make sure that it is not stuck open or closed. A PCV that is stuck closed will result in excessive crankcase pressure and excessive blow-by gases into the combustion chamber. The operation of the engine electrical system can impact the vehicle's drivability and performance. Low battery voltage can cause low current in the primary ignition circuit that can cause lower than normal firing voltages and engine misfires. Battery testing requires extreme caution, and you must use safety glasses, gloves, and protective clothing when charging and testing batteries. Batteries should be tested for their state of charge with a hydrometer or voltmeter and their ability to hold a charge using a load tester. Starter draw tests can isolate problems in the starter circuit that may be the cause of hard starting complaints. Generator output tests can show problems with the operating output of the alternator and should include tests to see if output is reduced as additional loads such as lights, defoggers, and air conditioning are turned on. Simple as it may seem, many of the generator and battery problems are just the result of a misadjusted generator drive belt. And keep in mind that voltage drop tests are essential when working on any circuit that can affect drivability. Whether you're diagnosing a starter, generator, engine control, or any other circuit for that matter, unwanted resistance will cause problems by restricting current flow and lowering the available voltage. As we have seen, the ASE A8 engine performance test will cover all of the interrelated systems necessary to make a vehicle perform properly. If you're uncomfortable with any of the areas we've covered in this video, pick up one of the excellent ASE test guides or training manuals on automotive engine performance and take the time to further prepare for the test. Thanks for watching, and good luck on the test.